Hi all, today we are going to continue the session on error handling mechanisms. Let's see the error detection mechanisms like checksum and cyclic redundancy check CRC. First, let's see how checksum can be used for detecting the errors in transmission. In checksum mechanism, first we will divide the data into k segments where each segment should have m bits. In the center side, the segments are added using 1's complement arithmetic to get the sum. The sum is complemented to get the checksum value. This checksum value is added as a segment in the data being sent. At the receiver side, all received segments are added using 1's complement arithmetic to get the sum. The sum is again complemented. If the result is 0, the received data is accepted. Otherwise, the received data is discarded. That means there is an error in the received data. Let's understand this concept with an example. This whole thing is our data. So we have divided our data into 4 segments where each segment having 8 bits, that is 8 binary is there in each segment. 1001, 1001 is 8 bits, 1111, 000010 is 8 bits, 00100 is 8 bits, 1000010 is 8 bits. So we have divided the entire data into 4 segments. K represents the number of segments and M represents the number of bits in each segment. So in the center side, we will add the segments together using 1's complement technique. So first let's add the first 2 segments together, 1001100 plus the second segment, that is 1110010. So we have to do the binary addition. 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 1 is 0 with the carry 1. So if there is a carry, we have to add that also with that resultant value. So 101111 plus this 1. So 1 plus 1 is 0 with the carry 1, 1 plus 1 is 0 with the carry 1, 1, 1, 1, 1, 1, 0. So now we got the sum of first 2 segments. So with this result, we have to add the third segment, which is 001001000. So add the sum of first 2 segments plus the third segment. 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 1 is 0 with the carry 1, 1 plus 1 is 0 with the carry 1, 1 plus 1 is 0 with the carry 1, 1 plus 1 plus 1 is 1 with the carry 1, 1 plus 1 is 0 with the carry 1, 1. So now we have got the sum of first 3 segments. So with this sum, we have to add the fourth segment, which is 10000100. So we have to again perform binary addition. 0 plus 0 is 0, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 1 is 0 with the carry 1. So we have to again add this carry to the resultant value. So 0 plus 1 is 1, 0 plus 0 is 0, 1, 0, 0, 1, 0, 0. So now we got the sum. In order to get the checksum, we have to take the complement of this. So for taking the complement, change the zeros into ones and ones into zeros in this sum value. So 1 is changed into 0, 0 is changed into 1, 1 is changed into 0, 0 is changed into 1, 0 is changed into 1, 1 is changed into 0, 0 is changed into 1, 0 is changed into 1. So just take the complement of some value to get the checksum. So now this checksum is generated. So this checksum is sent to the receiver side as a new segment. In the receiver side, the receiver system will perform the addition of all the received segments. So there also it will add up the first 2 segments together, 1001 plus 1110010. The same procedure is repeated, and finally we will get the same sum here, that is 001000101. So after getting the sum of all the received segments, to that sum we have to add up the checksum value. The checksum value is 1101110. So just add that checksum value with the sum that we got by adding the received segments 1101110. So just add these 2 values together, 1 plus 0, 1, 0 plus 1, 1, 1 plus 0, 1, 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 1 is 1. So after getting the sum, just complement that sum. If we are getting the complement value as 0, then we have to accept that data. If it is a non-zero value, that means the data is corrupted during transmission and we have to discard the data and we will ask for retransmitting the data again. Next, let's see the next method to detect errors. It is called as cyclic redundant check. In cyclic redundant check, we have to perform some sort of division in cyclic order. Here the data is cyclic and we have to add some extra bits, so it is called as redundant. And after that, we have to check whether the value is correct or not in the receiver side. So it is called a cyclic redundant check. Here we are doing some sort of binary division. In CRC, a sequence of redundant bits called cyclic redundancy check bits are appended to the end of data unit so that the resulting data units become exactly divisible by a second predetermined binary number. At the destination side, the incoming data unit is divided by the same number. If at this step there is no remainder, then it is assumed that the data is received correctly. If there is a remainder, then we will reject the data and we will ask for retransmitting. So let's understand this concept with a problem. So this is the original message that we want to send, 10100000. In CRC, we will use some generator polynomial to generate the CRC value. So the CRC generator here is x cube plus 1, so it can be rewritten as 1x cube plus 0x square plus 0x raised to 1 plus 1x raised to 0. That is, the coefficient of second degree and first degree is not defined, so it can be assumed as 0. So the value is 1x cube plus 0x square plus 0x raised to 1 plus 1x raised to 0. So we can get the CRC generator value of the coefficient of the polynomial, that is 1001, which is a 4-bit number. So if we are using a 4-bit CRC generator, then we have to append 3 bits to the original message. If we are using a 5-bit CRC generator, then we have to add 4 bits to the original message. So in general, if CRC generator is of n bit, then we have to append n-1 zeros in the end of the original message. So our original message is 101000. So we are using a CRC generator which is called as 1001, which is a 4-bit number. So if we are using a 4-bit number as a CRC generator, we have to append 4-1 bits to the end part of original message. 4-1 bit means 3 bits. So I am adding 3 zeros to the end of the original message. So now the original message is set as 101000 and the 3 appended bits 000. So we have to now perform the XOR operation to the value. So now we have to perform the XOR operation with the CRC generator value. I hope you may remember the XOR gate in logic system design. So if both inputs are 0, the output will be 0. If both inputs are 1, the output will be 0. All other cases, the output is 1. So if both the inputs are same, the output will be. So in the center side, first we will perform the XOR operation cyclically. So along with the data from the first bit onwards, I am writing the CRC generator value, which is 1001. This at represents XOR operation. So 1 XOR 1 means 0, 0 means 0, 10 means 1, 0 XOR 1 means 1, then the remaining are zeros. Just write down these values. Then check for the first bit which is having 1 value. So this 0 is discarded, this 0 can be discarded. So the starting value is from here. So below that particular bit, write again the CRC generator value. So 1001. Then again perform XOR operation. 1 XOR 1 is 0, 1 XOR 0 is 1, 0 XOR 0 is 0, 0 XOR 1 is 1, then the remaining zeros. Then again check for the first bit which is having 1. Exactly below that, again write the CRC generator value 1001. Then again perform XOR operation. 1 XOR 1 is 0, 0 XOR 0 is 0, 1 XOR 0 is 1, 0 XOR 1 is 1, then the remaining zeros. Again check for the first bit possessing 1 value. So it is here. So exactly below that write the CRC generator value, which is 1001. Again perform XOR operation. 1 XOR 1 is 0, 1 XOR 0 is 1, 0 XOR 0 is 0, 0 XOR 1 is 1, then 0. Again perform XOR operation. 1 0 0 1, 1 XOR 1 is 0, 0 XOR 0 is 0, 1 XOR 0 is 1, 0 XOR 1 is 1. So when to stop this particular cyclic process is check whether there is at least 4 bits from the first bit having the 1 value. So after this 1 value there is only 1 bit left, so we can stop here. If there is more than 4 bits available after this, then we can perform XOR operation again. So now we have to take the last 3 bits. Why we are taking 3 bits? Because the CRC generator is 4 bits, so we have to take the n-1 bits as CRC generator value. So 4 minus 1 is 3, so I am taking the last 3 bits, which is 0 1 1. So this 0 1 1 will be added with the original message. The original message is 1 0 1 0 0 0 0 0 plus this 0 1 1, which will be equal to 1 0 1 0 0 0 0 0 1 1. So this message is transmitted to the receiver side. So in the receiver side we will again perform the same XOR operation from the first bit till the last bit. So 1 0 1 0 0 0 0 0 1 1 XOR 1 0 0 1. 1 XOR 1 is 0, 0 XOR 0 is 0, 1 XOR 0 1, 0 XOR 1 is 1, then the remaining 0 0 0 1 1. Then check for the first bit possessing the 1 value. So here below that write down the CRC generator value 1 0 0 1. Remember the CRC generator value is shared with both the sender and receiver. This CRC generator value is not encrypted. It is known to both sender and receiver. When sending the data, the receiver will also know that the CRC value is 1001 because that data is shared by the sender to the receiver side. That is why we are directly using this value. So we are again performing XOR operation. The first one is here. So below that write down the CRC generator value. 1 XOR 1 is 0, 0 XOR 0 is 0, 1 XOR 0 is 1, 0 XOR 1 is 1, 0 1 1. Again perform the XOR operation. The first one is here, so write the CRC generator value below that 1 0 0 1. Then again perform XOR. 1 XOR 1 is 0, 1 XOR 0 is 1, 0 XOR 0 is 0, 1 XOR 1 is 0 1. Then again check for the first bit possessing the 1 value. It is here, so write the CRC generator exactly below that. So 1 0 0 1 XOR 1 0 0 1. So it will be 0. So if we are getting the final value of 0, then we can say that the data is correct. That means the data is accepted. If it is a non-zero value at the end of this process, then it will discard the received data and it will ask for retransmission. So this is how cyclic redundancy check is used for error detection. Thank you.